Hola, muy buen día a todos. Good morning, everyone. And thank you very much for this invitation to talk about my work here. I speak a little Spanish if you want to speak to me in Spanish later, but mostly the talk will be in English so that everyone can participate. And I'm going to talk a little bit about my work and the work that I've been doing with my group for a few years now. A lot of students have participated, and I think in the spirit of this conference, I'll try to show you a little bit of everything and a lot of what we have been doing, and it's something that a lot of people can participate. So there's still a lot of room for new projects and new collaborations. So if you're interested in this in any way, we can talk during the discussion session. And as you can see from my title, I'm going to talk about how fast do galaxies die and probing quenching timescales in the Green Valley. Not only quenching, but you see mostly galaxy evolution and how galaxies change star formation properties. As I said before, this is a big collaboration with a lot of people, especially students in my group. Karim Menendez del Mestre, who's also a professor in our university, and Camila and João Paulo, who were previously graduate students and collaborators from Caltech and other universities as well. So I think this is going to be a very general statement here. Galaxies form, galaxies evolve, and we have a pretty good idea how that works in general because we know how that functions as a function of time. Galaxies form within dark matter halos. And the interesting thing is that the distribution of galaxies in the universe is something that we can definitely understand really well, how they are distributed, how they form clusters, massive clusters and isolated galaxies, voids, etc. But something that we still do not understand very well. Of course, we do not know what dark matter is, but I'm not going to go there. We've seen a lot of talks already this week about it. But my interest is actually the baryons. I know the baryons form a very little portion of what's composing a galaxy. But as you can see, there are a lot of physical processes that happen within a galaxy that depends a lot on the baryons, the feedback, star formation. You need to understand exactly how those atoms interact within the gravitational field and all of the thermodynamics that goes into it, how and it's a very complicated process, as you can see there in this illustrious video. There's a lot going on that we need to be able to understand in detail so that we can actually understand how galaxies form. And in principle, my interest here is how they lose that gas and stop forming stars. We do know that this is something that needs to happen in a way because we know there's a Green Valley. I'm going to talk a lot about Green Valley, and the idea here is just that you have two peaks in galaxy distributions. You have the red peak, you have the blue peak. We call them usually the blue sequence or the blue cloud, the red sequence. But there's definitely a dearth of galaxies in that middle there. So we do not have a lot of galaxies with intermediate colors. We do know that blue galaxies are young, they're still forming stars, red galaxies are not. And the fact that you have a lack of galaxies in between means that these galaxies must be moving pretty fast through the Green Valley. So it's not just a matter of exhausting the gas, you end up your fuel tank and you do not form stars anymore, but you actually need to actively get rid of that gas somehow. So galaxy quenching is something real and something that we need to understand to fully understand how galaxies evolve. And that exists not only, as you can see here, at low redshift, but also at high redshift is something that you can already see that bimodality happening. So how does that happen? And one very common way to explain that is definitely AGN. You have a very powerful feedback from galactic nuclei that either pushes away the gas or it heats the gas so it doesn't fall back within the galaxy. And we definitely see a lot of AGN within the Green Valley. So I'm putting there some works by Martin and Andra. And you can see that whether you select it in X-ray or optical lines, you're definitely going to see a lot of galaxies in the Green Valley with a lot of AGN. So probably the AGN are participating in that process somehow. And also Kevin Showinski has done a very complete work in 2007 trying to show that um, that process in terms of different types of AGN and how that can connect to galaxies evolving within the color magnitude diagram. Usually you can see that in the top plot there, different types of AGN and different types of galaxies at different colors. So you start with some distribution and you move up depending, and the AGN evolves with that. So probably the AGN has something to say about galaxies quenching for sure, because it can drive away the gas and it can heat it up. At the same time, we also know that there are a lot of environmental effects. I'm just showing one example here. One of the most popular, which is ram pressure stripping. So galaxies falling into a cluster, they're going to interact with the intercluster medium, that very hot gas, and through some sort of interaction, and it takes a lot of hydrodynamics, the gas can be removed from the galaxy, and once the gas is removed, you do not form stars anymore because you don't have the gas to form stars anymore. We definitely see that in H1 or in the optical, as you can see on the right here. And there are other environmental effects, harassment, strangulation. We can talk about that in minute detail if you want. But the idea is that galaxies, when they fall into clusters, usually they're going to stop forming stars. We know that, we've known that for a while, but understanding the details of the physical processes involved is much more complicated. The fact is, there are a lot of processes that may actually quench star formation in a galaxy, and this is one example that I'm showing here. I like this plot from Peng et al. 2010, because they show that the fraction of quenched galaxies, meaning the fraction of galaxies that are not forming stars, it depends very strongly either on mass or the density. So we know that galaxies in dense environments are usually quenched, but as you can see in the x-axis here, also the fraction depends strongly on mass. So even a massive galaxy in an isolated environment is also quenched. And you have maybe two ways to quench galaxies. Maybe it has something to do with interactions and AGN feedback. Anyway, it's a lot of things can happen that can quench a galaxy in a way. And when we look at the high redshift universe, we know that things were different back then. So for example, as we can see in the review by Madal and Dickinson here in 2014, we know that the universe was forming stars more rapidly in the past. So the universe was a more violent and more intense place in the past. As you can see here, you see that the rate at which the universe was forming stars per unit volume was at least a factor of 10 higher. So definitely there was more stuff going on, and that certainly affected galaxy evolution as well. And something that's very popular is the idea of downsizing, and you can look at it in many different ways, like the work by Daniel Thomas or Whittaker. We know that the processes in galaxies are moving towards galaxies of lower mass, either galaxy formation or whatever it is. The high mass galaxies formed very quick and quenched very fast. And now galaxies that are responsible for that sort of process in the local universe is mostly the low mass galaxies. Also something to do with galaxy evolution that we need to address when we try to understand this in a bigger picture. What we're trying to do here in this work is trying to understand the mass flux across the Green Valley, meaning galaxies that are forming and are moving through that intermediate place. And the way that we've done this for many years is try to model like a pipe. I like that analogy in the sense that if you only look at the red sequence or the blue cloud, especially if you look at the red sequence, you're going to see, for example, water falling into a pond, and the pond is growing, and you can understand that. But you're not going to see the process that the galaxy is going through. So if you want to understand that, we want to look at the Green Valley, the galaxies that are actually undergoing that sort of transformation in a way. And if we do that, then we're going to be able to measure, for example, following the idea of a pipe, we can measure how fast that water is flowing through the pipe or how much mass is going through the pipe. And if you do some sort of hydrodynamical analogy here, you can measure the flux as being the density of galaxies in the Green Valley divided by the time that they take to to cross that green valley. And measuring the number density is not very hard, or the mass density either way. We can count galaxies within the green valley, measure their masses, measure their number densities. That's usually easy. The hard part is measuring quenching timescales, so how long it takes for them to cross the green valley. And this is where this work comes in. The idea is that we're using spectroscopic indices to measure how fast those galaxies are moving. And basically, the main thing here, if you want, I can explain more during the discussion, but we're mostly using the 4,000 angstrom break, which is a proxy for the age of the stellar population, and the depth of the H delta absorption at 4,100 angstrom, which tells us a little bit about the recent star formation, because the absorption line there is mostly caused by type A stars. So when you combine those two, you can measure the age and how fast it has been forming stars in the recent past. And when you combine that, you have some sort of idea of the star formation history in these galaxies in the recent past, and the acceleration, how fast they're moving there. So if you model the star formation history, and this is a first step here, if you model the star formation history as an exponential decay as a function of time, as you can see there, let's assume it has been constant for a while and then it exponentially decreases. You can measure that exponential factor there, the gamma, by using that. You can use different values of gamma, and this is what you see in the bottom left plot. So you can have an idea how fast galaxies are moving. So a gamma of 20 gigayears to the -1 means a galaxy that is moving very fast, and a galaxy that's 0.5 gigayears to the -1 on the bottom of the plot means a galaxy that's moving slowly through the green valley. And when you fold that into your calculations, you can see how fast galaxies are moving through the green valley. And this is something that Chris Martin did in 2007. And especially those two bottom green arrows that you can see on the bottom right panel, they compare very well with the growth of the red sequence across similar redshift ranges. So that means that in general, this idea works very well, and you can measure the mass flux. What I did later in 2012 was try to measure the same thing, but for Z of 0.8 galaxies, which was an observational challenge because we actually need to measure a lot of absorption lines in high-redshift galaxies that require a lot of big telescope time. But we managed to do this for approximately 100 galaxies, more or less. And what we found out was that when you see the range of gammas, and when you compare that between high redshift and low redshift, you can see that there are more galaxies at higher redshift with higher gammas, meaning they're moving faster. So there are more galaxies moving faster through the green valley at high redshift, and fewer galaxies going slower when you compare that to low redshift. And when you can see this in another way, this is a plot of the density and the magnitude there on the x-axis. The idea here being when you compare the lines, which are the low redshift, and the squares, which are the high redshift. Red and black are just different ways of measuring that, but the idea is the same. You can see that in the green valley, galaxies tend to be brighter at higher redshift. So not only they're moving faster through the green valley, but also you tend to have more massive galaxies going through the green valley at earlier times. So that compares very well with previous results, for example, the buildup of the red sequence. And that's a very good example of downsizing. So what you can see is that the more massive galaxies are quenching earlier and going through the green valley earlier. And as time goes on, you build up the left side of the luminosity function of galaxies in the red sequence, which are the diamonds in that plot there. So you can see that you first quench the very massive galaxies, and then you quench the low mass galaxies as a function of redshift, as a function of cosmic time. So this is something that we knew before, but that was the first time that we actually saw this in action with the green valley galaxies themselves. So we could measure that the more massive galaxies were quenching faster at earlier times. A schematic view is something like this if you want to compare. So at high redshift, the galaxies that are moving from blue to red are the more luminous, more massive ones. And then you slowly build up the rest of the red sequence as time goes by in a slower fashion when you go to low redshift. The problem here is that we do not, this has nothing to do with actual physical processes. We're just measuring quenching timescales, but we're not saying anything about what the actual galaxies are doing. And this is something that we've been trying to do more recently. For example, trying to correlate quenching with other properties of the galaxies. And this is something that, for example, Kevin Chomsky did in 2014. They noticed that, for example, when you correlate with morphology, again, trying to do some very simple stellar population models, they found that usually the late types, meaning the spiral galaxies, were moving a little faster through the Green Valley, and moving a little slower. And the early types, the elliptical galaxies, were moving faster through the Green Valley. This is what they found there. But that required some modeling that depends a little bit on knowing previously what the star formation history of the galaxies was, and it's mostly done by placement on the colored magnitude diagram. But we managed to do that, and this is work by João Paulo Nogueira Cavalcante, who was a PhD student working in our group a few years ago. So what he did was trying to do that sort of measurement as I did in my previous work, doing that for Green Valley galaxies and looking at quenching timescales directly from the spectra of the galaxy. So we have a much better handle on the galaxy population there. And what he found was something very similar, that when you look at the quenching timescales, when you look at the left part of the plot there, you have mostly spiral galaxies, and the spiral galaxies have much longer quenching timescales. And when you look at ellipticals or even irregular galaxies, for example, as you can see in the galaxy morphology there in the x-axis, you see that the quenching timescales are much shorter. So the secular evolution galaxies that are not undergoing some sort of transformation are moving slowly through the Green Valley, and the other galaxies, the elliptical galaxies or irregulars, those are galaxies that usually undergo some sort of violent process, usually some sort of merger. Those move much faster through the Green Valley. He also worked a little bit on concentration, and as you can see there, this work by Chung and collaborators in 2012, I really like this one, because there seems to be some sort of dependence on the concentration within the central kiloparsec. So not only morphological transformation takes some part there and is important in some way, but also you need some sort of density within the center of the galaxy so that it quenches. That might have to do with AGN feedback, certainly transfer of angular momentum and driving a lot of material into the galaxy that has something to do with it. But it's very interesting to see how it depends very strongly. The fraction of quenched galaxies or galaxy colors depend very strongly on this threshold of about 10 to the 9 solar masses per square kiloparsec within the central kiloparsec. And this has been discussed, for example, by Barro and collaborators in 2013, that again, when you compare low and high redshift, at high redshift, you have some sort of compaction, galaxies get very compact, and the quenching has something to do with that. But at lower redshift, the gas pore quenching mechanisms, as you put it, moves galaxies slower through that diagram over there. So again, we try to measure the quenching timescales as a function of compactness of the galaxy. And as we can see, the quenching timescales, again, are much longer for galaxies that are, let's say, normal. And the compact galaxies, especially the ultra compact galaxies, have much shorter quenching timescales. So they move much faster through the Green Valley. And that can be seen again in that plot there. This is a comparison with simulations that also show that the galaxies, the ultra compact galaxies, when they quench much faster. So you can see the time evolution of star formation rates is much more violent for the compact galaxies than for the other galaxies. This has definitely a lot to do with the decrease in the number density of compact galaxies. Compact galaxies, we know that they were much more common in the early universe, but then they became much rarer later on. So this was done by Aldé Charbonnier and other collaborators, including myself. She was a postdoc again in our group, and we measure the evolution of the compact galaxies in the as a function of redshift. There's a lot of variation there, but we do see still some compact galaxies at low redshift. But again, this variation in the number density of compact galaxies probably has a lot of relation with the downsizing in quenching timescales that we have seen in works like the one by Nogueira Cavalcanti and collaborators about 2 years ago. And finally, something else that he worked on which was interesting, was using using narrow band surveys to see if we can do that, not by taking actual spectra, but by measuring the narrow bands within the galaxies. If the band is narrow enough, they can measure the variation within the absorption lines. Maybe we can do it. And so he took the narrow band data from J+, which is a narrow band survey, and he showed that he was able to measure the quenching time scales very accurately when you compare it, for example, with the Sloan spectra. So again, it's something that if you have a large enough sample with narrow band, it's not going to be as accurate, but at the same time, you have much higher, much richer sample and much higher statistics. So maybe we can do it more efficiently. And finally, something that I would like to say to finish is, what about realistic star formation histories? Because so far we've been talking about star formation histories as if galaxies were just quenching in an exponential time scale. And sure, this is an example from a simulation. We know that some galaxies remain sometime in the blue cloud, as you can see there, and then they move on to, at lower redshift, they move on to have lower star formation rates. And that's the typical way, the way that we imagine galaxies. But some galaxies have much more complicated star formation histories. They move up and down, they reburst, they start forming stars again, and then they quench again, and they go back and forth between red and blue, and it can be very complicated. The idea, so what we try to do here is try to take into account those stellar population models and see, can we recover the physical parameters from those galaxies? So let's say that we know all of the properties of the galaxies from the simulation, because it's a virtual galaxy, it's not a real one. But let's try to put some stellar population models on top of that to see what kind of spectra we would have for that galaxy at different times, of course, when it's bursting, when it's quenching. And let's, on top of those fake stellar population models, let's do some photometry and spectroscopy and see if we can recover the physical parameters of these galaxies by artificially measuring those galaxies. This is what we did in that paper from 2017. And as you can see in that plot there, the vertical axis is something that from the fit, so what we're recovering, and the x-axis in all of those plots is what we are, what the input is, so what the virtual galaxy actually looks like within that simulation. And we managed to recover things very well. And one thing that I would like to call your attention is to that plot F there. So as you can see, this is the spread there is very large, of course. This is something very difficult to measure, but this is what we call the SFA. SFA is star formation acceleration, which means essentially the time derivative of the star formation. So for the first time, we're actually being able to measure not only how fast stars are forming, but how that's varying as a function of time. And that not only for quenching, but for bursting as well. And we can do that for individual galaxies, of course, with a big error bar. But if we have enough galaxies, we can measure the behavior of a large enough sample of galaxies. So this is something that we do. So for example, in that diagram there, let's see how galaxies are moving through the color magnitude diagram. On the top, you have star-forming galaxies. On the bottom, you have quenched galaxies. And you can see that galaxies are moving both ways. But more interesting, we can do that, for example, let's separate between massive and less massive galaxies, or galaxies with more or less, or more with AGN or no AGN. And for example, we see that it's very dependent on mass, for example. So the quenching you can see on the left diagram, the quenching depends a lot on mass. So you have much more quenching for the low mass galaxies, as you can see, and the high mass galaxies are more stable, let's say. And again, if you look at AGN versus no AGN, you see that the galaxies with AGN are usually quenching faster, which is to be expected, right? So the AGN helps quench star formation, but this is something that we can measure directly from the spectra of the galaxies, which is very interesting. And now we're not talking about fake galaxies anymore. This is actual data from SDSS. We've done that with the environment, so we see that there are very different behaviors for satellites versus central galaxies, for example. Again, this is to be expected. We know that from simulations, the satellites are going to be quenching in a different way from central galaxies. But we can measure that directly in those galaxies, not only for low redshift, but for high redshift now as well. This is beautiful work done by Behnam Darvish. And finally, this is my last section of the talk. And this is work that has been just submitted to monthly notices, work done by Camila de Sá Freitas, which is a master's student who just graduated in our group. She's starting a PhD at ESO now. And she managed to see that those quenching time, not only quenching time scales, but star formation acceleration depends very strongly on the morphology. This is something that we had seen before, but we can see now not only inside the green valley, but across the whole color magnitude diagram. And we can see that galaxies have different behaviors, not only within the green valley, but even within the blue cloud as well. So the elliptical galaxies, which are the red circles there, they're quenching more than the spiral galaxies. So higher SFA values means more quenching, and negative stuff SFA means more bursting. As is to be expected, the very blue galaxies are typically bursting, but even within the blue cloud, the elliptical galaxies are already quenching. And this has a lot to do not only with the morphologies of the galaxies, but also galaxies that have been classified as symmetric and asymmetric. We've done a lot of work based on deep learning of the morphology of the galaxies. And if we look just at the ellipticals, which is on the left, we see that the galaxies are typically quenching, and they're not very asymmetric. But especially on the right, we see the spiral galaxies. And what you can see there is that the spiral galaxies, the symmetric spiral galaxies on the bottom, they're quenching, but the asymmetric galaxies are bursting across the whole color magnitude diagram. So on the x-axis, we have color there. And typically the galaxies that are more asymmetric, the asymmetric spiral galaxies, they're quenching. So we can see that behavior depends very strongly on how symmetric the galaxy is. And we put together, of course, there's more stuff on the paper, but we try to sum it up with a very, very schematic diagram of how galaxies evolved. Again, if we have the symmetric spiral galaxy, nothing very violent is going on with it. It's just secular evolution. And there's this low track that moves it from blue through green to red. But if it undergoes, for example, a major merger, it can get very messy, and very quickly it starts. There's a quick burst, of course, but very quickly starts to quench and move through a fast track because it's losing gas very fast. It's moving fast through the green valley to the red sequence, with possible merger, the possible galaxies going the other way around, meaning rejuvenation, asymmetric galaxies that are going through the green valley back to the blue cloud, a little bit of galaxies going the other way. So this is something that was not possible before because we're only using very simple star formation history models that assume that galaxies were uniformly quenching, but now we can include bursting within that scenario. This is just a summary to summarize my conclusions. The galaxies are bimodal, fast quenching, we knew that, but we found that there are different processes going on in high Z. Galaxies are quenching faster. That depends a lot on the structure of the galaxy, as we have seen. And especially there's all sorts of combination between mass structure, mass morphology, inner structure, environment, et cetera, et cetera. I'm going to finish by saying that this is just the tip of the iceberg. So I think there's a lot more going on here. And as I said in the beginning of the talk, there's a lot of room for improvement. There's a lot of ideas that we're having for new projects, taking into account a lot of the new data that's coming on. And especially the future is very promising because we're going to have, for example, the Mosaic instrument on the ELT, which is going to be able to look at galaxies that are down to 27th magnitude. And this is very ambitious, of course, but it's definitely possible, something that we are predicting that we can do in deep surveys. So we're going to be able to look at absorption features of galaxies of 27th magnitude. So we can look at galaxies that are much fainter than L star at high redshift, redshift 2 and 3. So we're going to be able to examine that process going on not only at low redshift, but very deep at high redshift, Z's of 2 and 3, peak of star formation in the universe, and see in great detail how that process is evolving over the last 10 billion years or so. So if you're interested, I hope you enjoy this talk, and I think there's a lot more to discuss. I hope you have questions, and I'll be happy to discuss this a little bit with you. And once again, thank you very much for the invitation. I hope you have enjoyed this, and I hope you're enjoying the event as a whole.